last time we already started to discuss how to use the integral to compute the arc lengths. Now just to recall this, so if we have a function which is whose derivative is differentiable, on AB, and we are interested in finding the length of the curve of this function f from A to B, then last time we have derived the following formula. So this arc length can be computed by the square root of 1 plus dy over dx square dx. And we saw last time already that because of the more complicated nature here of this formula, in particular the square root, there are quite a lot of functions, easy elementary functions, where we are not able to compute the arc lengths. So last time I showed you several examples. One example was y is equal to sine of x, x from 0 to pi. So what you want to know here is you have this curve here, and you want to know what is the length of this curve here. Last time we saw that the integral we encounter, if we plug it into this formula, we cannot solve it. So, but we saw that Maple can solve it. So if you know more functions, you can solve it. So but the only thing you can do in order to find this, the arc length is approximation. So you can. You are right. F is, I should say, continuous. Thanks a lot. I wanted to say continuous, not differentiable. So I need that the derivative exists and is continuous. This is the important thing. Then we can use this formula, so-called arc length formula, to compute the arc length of a function. And we saw already last time several functions like this one, where we are not able to compute the arc lengths because we cannot solve the integral here. So the only thing we can do if we want to find the length of this curve here, we can only do approximation. So we write down the integral and we use some of the approximation rules we have learned last time, like Simpson rule. You choose a large enough n, and you use Simpson rule in order to find an approximation of the length of this curve here. Unless you know more about functions, because we saw that Maple is indeed able to solve this integral by expressing it in terms of so-called elliptic integrals. And if you use Maple, because Maple has knows how to compute the functions which are involved in the antiderivative of this function here for sine of x, and of course you can also use Maple to evaluate this. So this was one example. Another example was the hyperbola. So if you consider the simplest hyperbola, then we saw last time that also here the arc length cannot compute it, because once more the integral we encounter here is too complicated. So the only thing we could do is again approximation. Another example, ellipse. Okay, so if we want to find, so what we want to find here is the arc length of the ellipse. You should notice that this is a more complicated question than finding the area inside the ellipse, because for the area we have a formula. For the area we have pi times a times b. Now, what we want to find now is the circumference of the ellipse. So I didn't write last time the integral down, so maybe I should do this. Of course, it's enough if we just consider this part here and then multiply with 2. So we solve this first for y, and we are just interested in the positive solution. So you have this is b square minus b square x square over a square. You have the root here, so you have b. Times, we assume that a and b are both larger than 0. I don't have to say this. So 1 minus x square over a square. And what we need for the formula is dy over dx, so we have to differentiate this. So you see dy over dx is equal to, so 1 over twice the square root, 1 minus x squared over a squared. Then we have from the inner derivative, we have a minus 2x over a squared. So you see, if you plug this in, what you get is indeed a quite complicated integral. Actually, we just have to consider the case x from 0 to a, and then 4 times. 4 times the integral from 0 to a. And then what we have here is the square root of 1 plus. Okay, and we have to square this. So we have b squared over a to the 4. And then we have x squared over, and what we get here is 1 minus x squared over a squared dx. So this is the integral we have to solve if we are interested in the arc length of the ellipse. Okay, so we can simplify this a little bit. So we have 4 times, and then we have the integral from 0 to a. So we use a common denominator. So we have here a to the 4 minus a squared x squared. So we can write here a squared, and then we have a squared minus x squared. And then we have here the same. So we have a to the 4 minus a squared x squared. But we have also plus b squared x squared dx. So you see that this is equal to, okay, so actually we can take out a squared here. So we have 4 over a, and then the integral from 0 to a. And what is left now is, this is, okay, so we have the square root of a to the 4th plus, and now we can write this as, let's say, b squared minus a squared x squared over, and here we have the square root of a squared minus x squared. Okay, so you see that dx. You see that the real problem we have here, because it somehow still looks like manageable, because we know that if we have an integral which involves something like 1 plus x squared and so on, normally what we use is the method of trigonometric substitution. But actually the problem is that you have here a factor, okay, which is different from this one. Okay, so actually this integral is not, we are not possible to compute it unless there is only one special case which is easy, namely if this coefficient here is equal to 0. Okay, because if this coefficient is equal to 0, so a squared is equal to b squared. This case is more easy, okay, because in this case the numerator is getting more can be greatly simplified. Okay, so you have here only a squared. You take it out, so you have 4a times the integral from 0 to a, and then we have dx over square root of a squared minus x squared. And if you use here, you can indeed use trigonometric substitution. If you use trigonometric substitution here, what you will get is that this is equal to the usual formula you know for the circle, but for the circumference of the circle. But in the general case, if okay, so you see that in order to find the circumference of the ellipse, what we have to solve once more is this integral here. You see that in the special case where a squared is equal to b squared, okay, because this term here cancels out. In this situation, the integral is getting much more manageable, because in this case we have such a type of integral which we can solve. But in general, if a squared is not equal to b squared, the main problem we have is that the coefficient of x squared is different here and here. So here the coefficient is -1, and here the coefficient is b squared minus a squared. That's why we cannot solve it. If you remember last time, because I showed you Maple is able to solve it, Maple will write this in terms of elliptic integrals. And if you remember what last time, I showed you the definition. I checked the definition in Maple for the elliptic integral. And if you remember it, roughly remember it, it was roughly something like this here. So the definition of the elliptic integral is the square root of 1 plus k squared x squared over the square root of 1 minus x squared. And the reason why as I have explained last time, why those new functions are defined, so-called elliptic integrals, just coming from this problem here, solving this integral here. This was a historical problem to find the circumference of the ellipse, which generalizes the circumference of the circle. The circumference of the circle was known a long time. The circumference of the ellipse turned out to be a hard problem because the integral here is not solvable. So what has been done already a long time ago is, okay, you say this is a new function. Okay, more or less, this is a new function. And then you first accept this function, like in high school you have accepted sine and cosine. Okay, in high school you have learned sine and cosine. At some time you accept it and you say, okay, I know those functions. The same has happened here already 200 years ago. So we define a function which is related to this integral here, and we accept this function, and then we can solve it. Okay. So this is just the reason why I mentioned it is just interesting because. It's just an interesting issue because several new functions are coming out from the problem of solving the arc-length problem for certain standard functions, like here, or finding the circumference of the ellipse. We saw that for the hyperbola, I showed you last time what Maple is putting out for the integral of the hyperbola. Also, the hyperbola, once this problem is solved, the hyperbola can be related to this problem and so on. Okay, but so. This is just to mention that as it is expected, this integral, the nature of the integral is more complicated. So even for simple curves, it's not possible to compute the arc lengths precisely. But what you can do, of course, always doing is using approximations or using Simpson rule or another rule, choosing a large enough n and computing the integral. But for this, of course, you have to a and b, okay. So otherwise, you cannot do it. So you have to give for a and b, you have to give certain values, and then you can find the arc length. There is no nice expression. So we saw for the hyperbola and for the ellipse, not possible. For the ellipse in general, unless the ellipse is a circle, only this case is manageable. But there is one so-called conic section left, which is the parabola. And for the parabola, indeed, it's possible to find the arc length. So the parabola is the only conic section where we can find the arc length. Now, so let's maybe compute this. Compute the arc length of the parabola. Okay, so let's assume we have given a parabola, and we want to find the arc length, for instance, x, let's say from 0 to 1. Okay, so here the integral is also not getting too easy, but much more easier. So you have the derivative is equal to 2x. So the arc length is equal to the integral from 0 to 1, and now you have 1 plus 4x squared dx. Okay, so this is kind of easy for us, okay, because here we know the method of trigonometric substitution will work. So what we do is 2x is equal to the tangent of theta. Because these kind of methods, okay, are now all standard for us. So whenever you encounter such an integral, once you see this type of integral, you don't have to think anymore because the methods are all standard now. So here, this is the standard substitution which we use in order to solve this integral. So you see that then the square root of 1 plus 4x squared gets the square root of 1 plus tangent square of theta. But 1 plus the tangent square of theta is the secant square of theta. And you and the square root is the secant of theta. And because for theta we have from minus pi half to pi half, we do not have to consider absolute value. So what we have here, this is the integral. Now we have also to find here, we have also to transform the boundary. So if x is equal to 0, theta must be equal to 0. If x is equal to 1, what we have is the inverse tangent of 2. We cannot express this as a beautiful number, so we just write this as alpha. So alpha is by definition the inverse tangent of 2. And now you plug this in here, so you have a secant of theta. What we have to do as well is to transform the dx. So 2 dx is equal to the derivative of secant is of the tangent is the secant square of theta d theta. So you plug this in and you get here 1/2. And then okay, and also this is easy for us. We solved this already. So because we found a recursion formula for secant to the n of theta, and we related secant to the n of theta to the secant to the n minus 2 of theta. So this can be related to the secant of theta by partial integration. And the secant of theta, we saw long ago that this is the ln of the absolute value of the secant of theta plus tangent of theta, or something like this. Secant times tangent plus secant square in the absolute value. Okay, so for this one, for this integral, you also have this in our textbook at the last page. You have a table of integrals. You can find there this integral. I just write out the result. So you have secant of theta tangent of theta plus ln. No, I said it wrong. It's the secant of theta, the integral, is really the ln of the absolute value of secant of theta plus tangent of theta. Okay, evaluated at 0 and alpha. And now you plug everything in. So you see at 0, everything is 0. So you have just to consider the alpha. The tangent of alpha, from its definition, we know is equal to 2. And the secant square of alpha is equal to 1 plus tangent square of alpha. But tangent of alpha is equal to 2, so this is here 5. And this means that the secant of alpha is equal to square root of 5. It's the plus root, not the minus root, because of the range we consider for alpha. And now you can plug everything in. So you have here square root of 5. You have here 2 plus ln. And here you have square root of 5 plus a 2. So you can forget about the absolute value. Okay, this is the final result. So you see that for the parabola, it's indeed possible to find the arc length. And this is the only conic section where it's possible, because for the ellipse and for the hyperbola, we saw we have problems to find the arc length. Okay, so here for the arc length, you also see that you frequently encounter integrals where you have to use the method of trigonometric substitution. That's why we have discussed this general method. Because the arc length formula is the square root of 1 plus the derivative of the function squared. Okay, so for many examples, natural tool then to use to solve the integral will be the method of trigonometric substitution, as you see here. In particular, whenever you have here a polynomial more or less. If you have a quadratic polynomial, then you can solve. So for a quadratic polynomial, we can compute the arc length always, because what you get here is something linear squared, and then we can use the method of trigonometric substitution in order to solve this. But even if we go to a cubic polynomial, it's more complicated. Much more complicated, the integral. So even for cubic polynomials, it's not easy to compute the arc length. Okay, now the next, we will see later on that the arc length function, the so-called arc length function, which is you have a given function, and you compute the arc length from some a to some x, where x is now a variable. This is maybe a little. I should write here another. So this is called normally the arc length function. This function will turn out to be very important for us later on. Now, you see that from the fundamental theorem of calculus, we know that the derivative of the arc length function with respect to x is just the integrand evaluated at x. Which gives you a nice way to memorize the arc length formula, namely, because if you multiply everything with dx and then square, then you see what you get is that ds square is equal to dx square plus dy square. Okay, formally, this is what we do is formally. So you multiply everything with dx and square it right and left. Then you get this here. Okay, and this like the Pythagorean theorem. Okay, so. Because what we wanna find actually is the length of the curve. Okay, so we have to sum up over those ds here, and the ds you can use the Pythagorean theorem to compute it like this here. Okay, so this gives an easy way to memorize the arc length formula. Namely, if you have to compute the arc length of a curve, okay, what you do is you sum up over those ds here. Okay, so you can think about like you have the curve here. And what you have to do is you have to sum up small distances over the curve, okay, from a to b. This is what you do here. So the ds you see actually here on the curve. And if you think about if you zoom in and you think about like you have a very small ds, which is you have a very small part of this curve, ds, which is almost linear. Okay, if here the interval is very small, then you have to compute this as okay, as a very small x and a very small y, and that's how this formula comes into life. So that's how you can memorize the formula. So you actually what you do is you sum up over this. This is sometimes called arc length element. So you sum up over these arc length elements, and every ds you can express by the Pythagorean theorem. Okay, and this will give you the formula. Okay, it's an easy way to. This is not a proof of the formula, but it's an easy way to derive the formula or to memorize it. You also see here that the arc length function, okay, is always larger or equal than 0, larger or equal than 1. Okay, so you see that the rate of change of the arc length with respect to x is always larger or equal than 1, and equal to 1 if and only if the derivative equal to 0. Now, this is something which is clear, okay? There's, the rate of change of the arc length function with respect to x will always be larger or equal than 1. This is something which is clear. This just expresses that here in this triangle, as x is getting larger and larger, ds is growing faster. Okay. If you look at this here, more or less it means that, more or less the reason behind this is that the length of this side is always larger than this one. This tells you that the rate of change must be larger or equal than 1, equal to 1, if and only if those two coincide. Okay, so, but this is just for later on. So the arc length function for us will turn out to be a very important function later on. Okay, so any questions to this? You should maybe, the arc length formula, you do not have to memorize it, okay? You just have to know this here, okay? So what you do is, if you want to find once more the length of the arc is, you sum up over all those, you divide it into very small pieces, and you sum up over those small pieces, and every small piece, the length of the arc is ds, the arc length element. And for this ds, you can use the theorem of Pythagoras to express it. So you do not have to memorize the arc length formula because it's you can easily derive it like this here. Now, a second application of the series of integration is computing surface areas of surfaces of revolution, of solids of revolution. Okay, so we have given a function on an interval. Now what we do is, so we look at this, as we have done before, we look at this region here. We rotate it about the x-axis. So we rotate it like this here. Okay, so what we get is a solid of revolution. And what we want to find now, because previously we were concerned with the problem finding the volume. Now what we want to find is the surface area, okay, of the resulting solid of revolution. Now, in order to do this, we just use the same approach we have used already in this lecture several times. So what we are going to do is we divide the interval AB into subintervals. On every subinterval, we approximate the original function by lines. So we approximate the original function by a polygon, as we have done in order to find the arc length. And then we rotate the polygon instead of rotating the function. And then we first compute, in the first step, we compute the surface area of the resulting solid of revolution, because it's more easy. Because if you have a polygon, if you rotate a polygon about the x-axis, what you get is kind of on every subinterval, what you get is some part of a cone, okay, which is called frustum. So on every subinterval, you have a frustum, and you just have to figure out first, okay, how to compute the surface area of a frustum. And once you have clarified this, you just sum up over the surface area of all those frustums, and then you let the subdivision tend to 0. It's always the same idea. Okay, so you approximate the original function by something which is more simpler. By dividing the subinterval, you look at the simpler structure instead of looking at the more complicated structure, and then you consider limits. It's always the same approach. And this is also true for all the approaches we have seen so far. So first you have to figure out how to compute the surface area, or how to define the surface area, better to say, for some easy objects. Now, this is again a question of defining things, not a question of computing things, because the surface area, we haven't defined the surface area of more complicated. We know all what the surface area of the sphere is, we know, or the ball is, we know all what the surface area of a cone is, and so on. But essentially, this is definition. You define it in a, because it's, for those simple objects, it's easy to define. But for a more complicated object, you have to think about a good definition. And what we are doing here is actually defining surface area in the first step, and then trying to figure out how to compute them. So let's first look at the cone, circular cone. So you have a disk as the base, okay, with some certain radius. And you have here this length here, which is called sometimes lateral height. Now, so what we want to do first is we want to define the surface area of something like this here. But the surface area is the so-called lateral surface, so it does not include the bottom. Okay, so only what you see here. Okay. So this is what we want to define first. Now, this you have done in high school. You have defined the lateral surface area of this kind of thing in high school, because it's quite easy. You slice it somewhere, you open it. Okay, what you see is, if you do this, what you see is a sector. Now, this length here is L, because it's kind of, you have sliced it here. So this length is L here, and the length here of the arc is just the length of the base circle. So you have 2 times r times pi, and here you have some theta. And what you want to know is now the area, the lateral surface area is equal to the area of this sector here. So, but you see that okay, theta is equal to 2r pi over L. Now, the area of something like this here is something we have already defined because this is the area problem. So the area is L squared times theta half. And you just plug this in here. So what you get is pi times r times L. So this is for this object, for the cone, for the lateral surface area of the cone. You will use this. We are going to use this definition. It's a definition. Okay. Now, what we are actually interested in, because if you think about a line here, okay, you just have a line here. You rotate one line. Okay. What you get, the object, what you get, okay, almost looks like this here, but it's just the bottom cut off. Okay. As I said, this is called the frustum. So if you have if you have just some part of the cone, so let's say this radius here is now R1, this radius is R2. No? We complete it. This is not very nice. So we complete it. So we just take the original cone and slide and cut off the top. Okay, so and we call again this length here the slant height to be equal to L, and let's call this here L1. Now, of course, it's now easy. Once we have figured out this, it's easy to compute the area, the lateral area of this here. And I said already, this is called frustum. Now, okay, so what we do is, okay, so we take the lateral area of everything, L plus L1, and we subtract the piece on the top, so minus pi times R2 times L1. Okay, and we just simplify this. Okay, so this can be written as we take out pi, and then for the rest we have R1 minus R2 L1 plus R1 L. This should be L1. I shouldn't delete this here. Now you see that between R1, R2, L1, and L you have certain relations. So you see that L plus L1 over R1 must be equal to L1 over R2. And this will help you to simplify this here. So you see that what is sorry, here is R1. Okay, so what you see here is this is LR2 plus L1 R2 is equal to L1 R1. Okay, so what you have is what we have here, this part here. So L1 R1 minus R2 is equal to LR2. So this one we can replace by LR2. So what we get here is this one is equal to 2 times pi times. So for this one we plug in this here, so we have an L, and then we have R1 plus R2. But this is kind of the if we divide this by 2 here, so if we write this as 2 times pi times L, then what we have here is R1 plus R2 half, and this we denote by R. This is kind of the average radius. So R is equal to R1 plus R2 half. So the formula which we get is that the lateral surface area of this kind of thing is the circumference, if you take here the average radius multiplied with the slant height. Okay, and we are going to use this now in order to find the so once we have figured out the surface area of this kind of simple object, we are going to use this in order to define surface areas of more complicated objects, of more complicated solids of revolution. Okay, so if we once more consider this kind of function here, now what we are going to do is our usual approach. So we divide the interval into subintervals, and on every subinterval we replace the function by a line. So this one, and this one, this one, and this one. So we replace the original function by a polygon, and we are going to rotate the polygon instead of the function. This will give us an object, okay, where on every subinterval you have a frustum, and you use what we have computed now, the surface area of the frustum, in order to approximate the surface area of the cone you get if you rotate these p's about the x-axis. Then we sum up over all those surface areas and let the subdivision become finer and finer. And in the limit, what we get in the limit, if the limit exists, okay, will be called the surface area of this surface of this solid of revolution. Okay, so what we have to do is, if we want to define the surface area, so we can approximate it here as okay, we have the sum I from 1 to n. Then, so here we are looking now at the i's interval. Now at the i's interval, so here xi minus 1, xi. The contribution from the i's interval is, we just saw the formula, so 2 times pi times. Now, what we have is the average radius, so f of xi minus 1 plus f of xi half, the average radius, multiplied with the length here of this curve here. So this is, so if I denote this point here by pi minus 1, and this point here by pi, then it's the length of the line between those 2 points. Now, last time we already expressed this as the square root of 1 plus. So we have, if we assume that the function is differentiable on the interval AB, we can use, we last time used the mean value theorem to express this as square root of 1 plus the derivative of f at some sample point. The sample point, if you remember it, is coming from the mean value theorem, multiplied with delta x. Okay, so we can plug this in here. So this is equal to the sum I from 1 to n, 2 times pi times f of xi minus 1 plus f of xi half times this object here, times the square root of 1 plus delta x. Okay, so what we get is this kind of approximation here. And now we let n tend to infinity. So the surface area will be defined as the limit n tends to infinity, the sum I from 1 to n, 2 times pi times f of xi minus 1 plus f of xi half times this here. So times the square root of 1 plus Now you see that, unfortunately, this does not look like a Riemann sum, okay? Because this is not, you have the delta x, but this is not some function evaluated at some sample point, okay? Now, but this kind of sample point which comes out from the intermediate values theorem is sandwiched between xi minus 1 and xi. And n tends to infinity, which means the subdivision is getting smaller and smaller. Okay, and what is important is that f is continuous. So under this assumption, I guess you are believing me that in the limit, you can replace this here also by f, evaluated at the sample point. This is something which you have to prove, actually, but it's not very complicated, because once more, the xi star, so the sample point is sandwiched between xi minus 1 and xi, and xi minus 1 and xi are getting closer and closer in the limit. So actually, it should be possible to, and the function f is continuous, so behaves kind of, if this is, behaves kind of like a linear function, and if xi and xi minus 1 are very close, you should be able to replace both of them by the sample point. And so what you get here is the function evaluated at the sample point times this kind of object times delta x. And now what you have is indeed a Riemann sum. So now you can rewrite this to a definite integral. So what you get is the integral from a to p, 2 times pi times f of x, square root of 1 plus the derivative of f of x square dx. So what we have to is, because this is a definition, okay, so we will define the surface area by this integral here. And in order to, actually, we will define it by this limit, or more generally, by this integral here. And in order that the definition makes sense, we have to assume for us that the derivative of f is also continuous. Otherwise, this integral might not exist. Meaning that there might not, if you use such a definition for the surface area, it might not be possible to define it like this, because the integral does not exist. Now you see also, actually it's maybe better to write this. First of all, if we substitute f of x to be equal to y, then you can rewrite this as the integral of f of a to f of p. Now 2 times pi. Now here the f of x becomes y by the substitution. So this is a new symbol now. And the dy is the derivative of f of x dx. So for dx, you have to plug in dy over the derivative of f of x. So what you get is 1 over the derivative of f of x squared plus 1, and then you have here dy. But this here, because you have to write this you have actually to write this in terms of y, not in terms of x. But the derivative is equal to dy over dx. So you just reverse it. Okay, so this becomes here. Because we have 1 over, so this becomes dx over dy. It's not a very precise proof, and actually something which you are missing here is you indeed have to, if you do this, you indeed have to assume that f is invertible, that the inverse of f exists. F must be 1-to-1, that this is possible, because here you need the inverse function. So this is what you have to assume in order to be able to do this kind of substitution. Now, if we, this is kind of convenient, because you see this is if we do not write the limit, okay, then the formula kind of becomes the integral. Here in this case you have 2 times pi times y, and then you have here 1 plus dy over dx square dx. Okay. Or you can also write this, if you forget about the limits, you can also write this as the integral. So actually what you have here is just those two here reversed. So you have 2 times pi times y, and then you have 1 plus dx over dy square dy. Okay, or you can merge this here, and this becomes here ds. Also this here becomes ds. Then the formula is the same, okay? But it's just the interpretation is different, because here you integrate with respect to x. Here you integrate with respect to y. So actually, and this is a way to memorize the formula. Okay, because if I maybe once more plot a picture. If this is A here and this is B, now, okay, if this is our function, so you can think about what you are going to do is, if you look at this formula, you integrate from A to B, and then what you look at are circles here. Okay, so what you are, if you fix this point here, you have here. If you just look at this point here, this point gets rotated about the x-axis. So the path which this point traces out is a circle. Okay, so you have the you have a circle here. Okay. Now the circumference of this circle is 2 times pi times y. Okay, and you have, for adding up, you have to use, because the thickness, okay, of this circle, okay, is given by the arc length element. So this is kind of how you can memorize this formula. Okay. So what you do is you're just adding up circumferences of those circles, but you have to take into account that the thickness of the circle is given by the arc length element. Of course, if you have a curve and you rotate it about the y-axis, okay, you get similar formulas. Just every time y replaced by x. So if you have a curve now not given as a function y is equal to f of x, but given as a function x is equal to g of y, then and you rotate it about the y-axis, you can give similar definition, and of course you get similar formulas. The only thing which differs is that y will be replaced by x. You just have to interpret it differently. Okay, so any questions to this? So in order to find the surface area of a given solid of revolution, what you have to do is more or less you plug into this formula here, and that's it. Now, this formula here is kind of better to handle compared to the arc length formula. The reason being that you have here an additional f of x. So this normally makes it more easy to work with this formula. Because the arc length formula didn't have this factor here. This is causing kind of trouble because you have a complicated integral. But now the situation is somehow more easy because of this f of x here. So indeed, it's possible to find the surface area of quite a lot of surface of revolution. So for instance, the ellipse is for the ellipse we cannot compute the circumference as we have discovered last time. But it's indeed possible if you rotate the ellipse about the y-axis to find the surface of the resulting solid of revolution, which is called the ellipsoid. Okay, so again we consider the ellipse. Now, what we are doing is we take the upper part of the ellipse, okay, only the upper part, and rotate it about the x-axis. So maybe I should delete the lower part. Now, what you get if you do this is a kind of egg, okay, and this kind of egg is called ellipsoid. So we are interested, okay, what is the surface area of the ellipsoid? Now, so first of all, the only thing we have to do is we have to plug into the formula. So first of all, it's enough if we go from 0 to a. Then we get everything twice because of symmetry. And then we have 2 times pi times f of x times 1 plus the derivative of f of x. Well, let's write this as dy over dx square dx. Let's write this as y. Okay, so we first have to find the derivative. Here it's maybe more convenient to use implicit differentiation. So if we take the derivative here, what we have is 2x over a square plus, now the derivative here is 2y over b square, and then we have dy over dx is equal to 0. So we see that dy over dx will be equal to minus, and then we have a square over b square, then x over y. No. Okay, so what we need is dy over dx squared. So this will be b to the fourth over a to the fourth. Then we have x squared over y squared. Now, because we have to plug it in here, so let's maybe look at 1 plus b to the fourth x squared over a to the fourth y squared. Okay, so this gives us a to the 4 y squared, and then we have b to the 4 x squared plus a to the 4 y squared. Now, y squared is equal to b squared 1 minus x squared over a squared. So we have to plug this in. So what we have is p to the 4th x squared plus, okay, now we have b squared a to the 4 minus b squared a squared x squared over, and here we have a to the 4, so a to the 4 b squared plus a squared b squared, not a minus b squared x squared. Actually, we can delete a b squared. Okay, so this will become a to the 4, then plus, and now we have b squared minus a squared over x squared over, and here we have a to the 4 minus a squared x squared. Okay, now we have to plug this in here. So we have twice. Now we have here the integral from 0 to a. Actually, this 2 pi we can take out, so we have 4 pi. And the y is the square root of this one, so the positive one, because we are just interested in the upper part. So we have p. So also let's take this p out. Integral from 0 to a, and now what we have here is the square root of 1 minus x squared over a squared multiplied with the square root of this one here. So what we have is the square root of a to the 4th plus b squared minus a squared x squared over. Now here we can take out so actually we can take out a to the 4. So what we have is a squared, and the rest is the square root of 1 minus x squared to the a squared. And this is now very good because you see that this guy cancels out here. So you see that okay, you can delete this guy here. And this is more or less the reason why it's possible to find the surface area of the ellipsoid. Okay, so what we have is 4 times pi times b over a square, and then the integral from 0 to a. Now, the square root of a to the 4 plus b square minus a square x square dx. And this part here is solvable, okay? So here you use the substitution square root of b square minus a square x is equal to the tangent of theta. Is a squared times the tangent of theta. So here you use this substitution here in order to solve this. I'm not going to do this. another way is to solve this. You just look at our textbook, last page, because there is the result for using general parameters, and you use the result there to plug it, and you just copy it, and then you plug in a and 0. But you see that one case here is in particular simple, namely the case where a square is equal to b square. Okay, and this is a square is equal to b square corresponds to the ball. So here you have a half circle. So, and fortunately, this case is very easy. In this case, you have that the surface area is 4 times pi times b over a square. Now, because this here becomes a square here, a square you can take out, so you have here b. And from the integral, you get the a here. Actually, a is equal to b. So you have this formula, the formula you have learned in high school for the surface area of a ball. And but also more general, it's possible to solve this. So this is quite remarkable because we cannot, once more, we cannot compute the length here of the ellipse. So we cannot compute the arc length because the integral is getting much too complicated. But it's if you rotate it about the x-axis, it's possible to compute the surface area of the resulting surface of revolution. Similar, you can also, like for the parabola, you can also find, in general, if you, for instance, consider the parabola y is equal to x squared, and you rotate it about the y-axis, similarly, you can just plug into the formula, but you have the role of y and x actually is interchanged, because you look at it from a different angle. The resulting surface of revolution is called paraboloid, and similar, it's possible to find the surface area of the paraboloid. Also, if you take the hyperbola, part of the hyperbola, and rotate it like x squared minus y squared is equal to 1, rotate it about the y-axis, you can also compute the surface area of the resulting surface of revolution, which is called hyperboloid. So all those kind of, this kind of ellipsoid, paraboloid, hyperboloid are all 3-dimensional generalizations of the conic sections, which you have learned in high school, and next semester we will spend a little bit time discussing them, because there are actually also other types which are not covered so far. Okay, so any questions to this? If there are no questions, so this will more or less finish what I wanted to teach about chapter 8, and next time we will, on Monday, we will start with chapter 10. So actually there are just 4 sections left, 10.1, 10.2, 10.3, and 10.4, and then we are done for this semester. And do not forget that next week on Thursday we have our final